In Part 5 of Lecture 1, we will discuss cache memory. Although cache memory is invisible to the operating system, it interacts with other memory management hardware. Furthermore, many of the principles used in virtual memory schemes, as we will discuss later in the course, are also applied in cache memory. On all instruction cycles, the processor accesses memory at least once to fetch the instruction, and often one or more additional times to fetch operands and or store results. The rate at which the processor can execute instructions is clearly limited by the memory cycle time, that is, the time it takes to read one word from or write one word to memory. This limitation has been a significant problem because of the persistent mismatch between processor and main memory speeds. Over the years, processor speed has consistently increased more rapidly than memory access speed. We are faced with a trade-off among speed, cost, and size. Ideally, main memory should be built with the same technology as that of the processor registers, giving memory cycle times comparable to processor cycle times. This has been always too expensive a strategy. The solution is to exploit the principle of locality by providing a small, fast memory between the processor and main memory, namely the cache. Cache memory is intended to provide memory access time approaching that of the fastest memories available, and at the same time support a large memory size that has the price of less expensive types of semiconductor memories. The concept is illustrated in the top diagram. There is a relatively large and slow main memory together with a smaller, faster cache memory. The cache contains a copy of a portion of main memory. When the processor attempts to read a byte or word of memory, a check is made to determine if the byte or word is in the cache. If so, the byte or word is delivered to the processor. If not, a block of main memory, consisting of some fixed number of bytes, is read into the cache, and then the byte or word is delivered to the processor. Because of the phenomenon of locality of reference, when a block of data is fetched into the cache to satisfy a single memory reference, it is likely that many of the near future memory references will be to other bytes in the block. The lower diagram depicts the use of multiple levels of cache. The L2 cache is slower and typically larger than the L1 cache, and the L3 cache is slower and typically larger than the L2 cache. This figure depicts the structure of a cache main memory system. Main memory consists of up to 2 to the nth power addressable words, with each word having a unique n-bit address. For mapping purposes, this memory is considered to consist of a number of fixed-length blocks of k words each. That is, there are m equals 2 to the nth power divided by k blocks. Cache consists of c blocks of k words each, and the number of slots is considerably less than the number of main memory blocks. Some subset of the blocks of main memory resides in the slots of the cache. If a word in a block of memory that is not in the cache is read, that block is transferred to one of the slots of the cache. Because there are more blocks than slots, an individual slot cannot be uniquely and permanently dedicated to a particular block. Therefore, each slot includes a tag that identifies which particular block is currently being stored. The tag is usually some number of higher order bits of the address and refers to all addresses that begin with that sequence of bytes. This figure illustrates the read operation. The processor generates the address RA of a word to be read. If the word is contained in the cache, it is delivered to the processor. Otherwise, the block containing that word is loaded into the cache, and the word is then delivered to the processor. A detailed discussion of cache design is beyond the scope of this course. Key elements are briefly summarized. We will see that similar design issues must be addressed in dealing with virtual memory and disk cache design. They fall into the following categories: cache size, block size, mapping function, replacement algorithm, write policy, and number of cache levels. We have already dealt with the issue of cache size. It turns out that reasonably small caches can have a significant impact on performance. Another size issue is block size, the unit of data exchanged between cache and main memory. As the block size increases from very small to larger sizes, the hit ratio will at first increase because of the principle of locality. The high probability that data in the vicinity of a referenced word are likely to be referenced in the near future. As the block size increases, more useful data are brought into the cache. The hit ratio will begin to decrease, however, as the block becomes even bigger and the probability of using the newly fetched data becomes less than the probability of reusing the data that have to be moved out of the cache to make room for the new block. When a new block of data is read into the cache, the mapping function determines which cache location the block will occupy. Two constraints affect the design of the mapping function. First, when one block is read in, another may have to be replaced. We would like to do this in such a way as to minimize the probability that we will replace a block that will be needed in the near future. The more flexible the mapping function, the more scope we have to design a replacement algorithm to maximize the hit ratio. Second, the more flexible the mapping function, the more complex is the circuitry required to search the cache to determine if a given block is in the cache. The replacement algorithm chooses, within the constraints of the mapping function, which block to replace when a new block is to be loaded into the cache and the cache already has all slots filled with other blocks. We would like to replace the block that is least likely to be needed again in the near future. Although it is impossible to identify such a block, a reasonably effective strategy is to replace the block that has been in the cache longest with no reference to it. This policy is referred to as the least recently used algorithm. Hardware mechanisms are needed to identify the least recently used block. If the contents of a block in the cache are altered, then it is necessary to write it back to main memory before replacing it. The write policy dictates when the memory write operation takes place. At one extreme, the writing can occur every time that the block is updated. At the other extreme, the writing occurs only when the block is replaced. The latter policy minimizes memory write operations, but leaves main memory in an obsolete state. This can interfere with multiple processor operation and with direct memory access by I/O hardware modules. Finally, it is now commonplace to have multiple levels of cache, labeled L1, cache closest to the processor, L2, and in many cases, a third level, L3. A discussion of performance benefits of multiple cache layers is beyond the scope of this course.